Hello, everyone. I am Zhang Yong from Beijing University of Science and Technology. I study structures, mechanical structures, and mechanics. But I'm not familiar with stages. However, I am very familiar with structures, so I can also exchange ideas with everyone. Perhaps because today everyone here has different backgrounds. So I think some of the things I say might seem too simple to some. To others, it might feel too deep. It's okay. We can exchange more later. I will try to explain as simply as possible. If anyone has something special to discuss, we can communicate further. I will introduce myself. I originally studied mechanics. If anyone is interested, we can exchange ideas later. You can scan the QR code in a while. Now I will start to exchange ideas with everyone. Everyone knows that our so-called stage, this stage I am standing, is for the purpose of giving speeches, performances, or reports. We built the slightly more prominent space by some effects. Of course, the current stage has already become very professional. It has become very professional. This stage we all know. It includes a general stage, basically a platform. This platform can face inward or it can face outward. Another part is these frames to support lights and so on. These frames, generally speaking, our stage structure mainly consists of these two parts. More parts actually are these supporting frames, the most important parts. In addition, of course, there are the stage entrance, curtains, and other things. For us, as stage structure manufacturers. Generally speaking, such a stage structure, what was just mentioned like this, such a front part can basically be understood as the functional load we need for our performance. Possible loads. There is also another kind, which are the two types mentioned later. The latter one, for our stage structure, if it's purely this kind of framework, there is usually no big problem, but if we need to close off for blocking effects, it has a windward side, especially for tall structures like TV towers. It can cause big issues, wind load. So in some areas, especially coastal areas and northern regions, if we have a lot of windshields, windshield curtains, or wind-blocking tarps, and there is wind, at this time, we must consider the wind load of the structure. What is this wind load? Basically, it is horizontal. Of course, if we have a ceiling, it could be upward. This is the wind load. Another thing is, such as earthquakes, the impact of earthquakes. The earthquake impact is transmitted through the foundation. When the foundation shakes during an earthquake, the foundation shakes and the structure above will move with it at this time due to the impacting time and other factors. Of course, the others. We generally consider things like the self-weight of the structure. What else? We must also consider wind and snow. Everyone knows there is a train station in Germany that collapsed due to snow. It has a flat roof, a very shallow flat roof, and it was crushed under the weight of snow. Snow's weight, this is especially true in northern regions. Here we can understand the earlier part as static loads. The earlier part can be understood as static loads. The later part we can consider as dynamic loads. The so-called static load is very clear. Once this load is applied, it generally doesn't change. Dynamic loads. Dynamic loads change with time. Dynamic loads are not as simple as imagined. What problems can occur with dynamic loads? First, it changes with time. For example, sometimes it gets bigger, sometimes smaller. Some people may say, why not just calculate with the largest value? It's not that simple. Everyone knows about swinging on a swing, right? A swing, that person in the swing system, is a typical dynamic system. When a person pushes with great force, as long as the frequency is right, the person can swing. This is the so-called resonance issues. So for our dynamic load system, we must analyze its dynamic characteristics, including resonance issues, which are more complicated than imagined. We won't discuss it here. Next, let's talk about how stage structures fail. What is the most easily imagined failure of a stage structure? Complete collapse. Complete collapse is disastrous. This is a typical. Does everyone see it? This is an example of a collapse of a frame structure. Actually, such a collapse. There are small signs at first. Small signs are like this. Caused by various reasons, I will talk about it later. The main reasons are manufacturing defects and unreasonable use and installation. Various factors can cause one of the components. For example, a small rod fails. It can cause the entire structure to redistribute forces. Redistributing forces will cause some rods to break. Some rods are broken. Here, the most typical is the local deformation of a member. For example, like this one. This is a typical light steel keel. The entire light steel keel hasn't changed. It hasn't failed. But this part failed. This part failed. If this is considered a rod, it completely fails. When this rod fails, you can imagine if one of the legs of the frame fails. The whole frame would be doomed. This is the idea. It starts from a very small part. So what's the second failure mode? It's called member fracture. This is rare in normal stage structures. Fracture problems are rare. Mostly it's collapse failure. Another failure is overall deformation beyond the limits. For example, due to the structure design, an unreasonable material choice. Many long materials of the structure may sag too much, but without collapsing, sagging too much. It can still cause the failure, affect our usage. Then there's the overall collapse. As mentioned earlier, common errors in design. First, incorrect material selection. The material is not suitable. Second, our mechanical calculations may not be thorough enough, or the formulas used are incorrect. Wrong calculation methods. These are all possible. Then there's manufacturing. Manufacturing problems we usually encounter. As mentioned earlier, incorrect dimensions. Shape and position tolerances exceeded. This is less common. More common are poor welding. Welding sometimes appears to be welded on the surface, but not welded inside, especially in critical areas. Actually, most of the welding seams are under very small forces, but if there's a problem in some key areas, there's nothing we can do. Then there's installation. I will discuss installation again later. The biggest problem with installation. The first issue is, for example, this column must be vertical. Gravity acts downward. Also, look at this pillar and beam. Both the upper beam and the lower beam have a central axis. The pillar also has a central axis. These two central axes must coincide. If they don't coincide, you can imagine. Where will the gravity press on the column? It won't press at the center. It presses off-center. If a column is off-center, will it fail? This is the logic. Then there's maintenance, a connection failure. The tension is obviously insufficient. Besides, there's also overloading. Overloading occurs. At this time, it's the biggest problem. Heavy objects suspended, their position is incorrect. Also, wind loads, snow loads, pressure not cleared, etc. These factors. Next, we all know. For most stages, they are temporary and semi-permanent. Many of them are built using temporary frames. These frames are modular. To save costs, allow reuse. To save costs, they are generally made into modular systems. More commonly, these are made as trusses. In fact, we call this truss. It comes from English. In fact, the definition of trusses in China is not exactly the same. Everything is made into modular systems. These modular systems are generally what we call trusses, trusses in English. Actually, the concept of trusses in English is very broad. But in China, trusses refer to these. When I say truss, you understand. In China, a truss refers to the type where the rods are hinged, not welded, only at the joints. Only at the joints do they bear force. Only at the joints do they connect. Only at the joints do they work. This is called a truss. This truss, the rods are generally straight rods. What's the advantage of this truss? It only experiences tension or compression, no bending. Many trusses are at our stage now. Now commonly follow what? The foreign definition, which refers to welded structures in China. In China's mechanical system, this is called a steel frame. We also call this a truss. just truss. We don't distinguish between them. We won't distinguish anymore. Such a thing. So the trusses characteristics. What characteristics does it have? Whether it's a steel frame or a truss, even welded steel frames, the bending stress on the rods inside is very small, very small. Bending stress generates because the hinge points are welded. It generates bending only because they are welded, due to installation or usage issues. So when it comes to trusses, we first need to talk about the materials for trusses. Now in our stage structures, the materials used for welding are generally divided into two types. One is steel and the other is aluminum. Many of our colleagues might think that steel and aluminum are the best, probably because they are cheap. Steel and aluminum are the cheapest materials, but it actually involves many performance aspects. There are issues regarding their use. Everyone might not fully understand. I will now briefly introduce to everyone. Steel is actually iron titanium alloy. You don't need to delve into this. Steel includes medium carbon steel, low carbon steel, high carbon steel. There are alloy steels, low alloy steel, medium alloy steel, high alloy steel, and so on. You don't need to mind these. Here's one thing for everyone. No matter what major you're studying, you should understand one thing. The main mechanical properties of steel include several things. One is called the yield limit. We take a steel column and pull it. You will see a curve like this. First, during this deformation, the force increases and it elongates. But at this point, what happens? It suddenly elongates quickly. This is called yielding. It has yielded. It's the same when we pull a noodle. Of course, the structure of the noodle is different from this, but it has yielded. Then it starts to harden again. It begins to strengthen. Then it breaks at the end. We call the slope of deformation and the slope of stress this thing we call the elastic modulus. This platform we call the plastic platform. So for our general structures, remember, for our steel materials and aluminum materials like these, we must use them within this range. It should not exceed this. It should not exceed the yield limit. What happens if it exceeds the yield limit? The deformation suddenly elongates. Your structure will become loose, won't it? That's not good, so everyone should understand this. Of course, it is even more unacceptable to reach this point. If it reaches this point, the steel structure will break. That's how it is. Of course, when we just selected this steel frame for steel materials, we also need to consider something else. We need to consider two things. One is called impact toughness, and the other thing is called weldability. Say many materials are good. For example, our high-strength steel is great. The strength of high-strength steel, we can now achieve 1200 megapascals, but its processing performance is poor, its weldability is poor, its shear performance is poor. So using it may not necessarily be cost-effective. Later, I will talk about something else. The second is what we call aluminum alloy. You don't need to mind aluminum alloys. You don't have to overthink it. I can tell you about aluminum. We use pure aluminum, there is pure aluminum, but pure aluminum is rarely used because it's too soft, and pure iron is rarely used too. However, we use aluminum alloys much more. There are several types of aluminum alloys. Aluminum alloys based on copper, we have the 2000 series, which includes copper. Adding manganese gives the 3000 series, adding silicon gives the 4000 series, etc. You don't need to care about that. Just look it up in the manual. Look up the strength level you need in the manual. Now this aluminum, its strength range can be very wide, but these two materials are the ones we commonly use. Of course, now there are also titanium alloys, but those are not mainstream. That's too expensive. But aluminum and magnesium, can aluminum and iron be used casually? No, they can't. Let me show you another set of data. Take a look. I've organized it. These are the main parameters we're talking about, affecting structural deformation and the strength of aluminum. Here are several parameters. The first is aluminum alloy. Look at its specific gravity. We see that its specific gravity is 2.7. Aluminum alloy is the same, while steel is 7.8. Did you see that? Aluminum is 3 times lighter than steel for the same volume. This lightness is important. It makes installation on-site much easier. Easy to install on the spot. but it also has some downsides. Let's look at the elastic modulus. Elastic modulus, which we call, when quantity is it? It's 210.70. It's 210.70. So it's 3 times smaller. It's 1/3 of steel's value. What does that mean? If I take a beam like this and a person stands on top of it, a steel beam with the same cross-section will be 3 times heavier than an aluminum beam. But the deflection of the steel beam is 1/3 of it, is 1/3 of the aluminum. So the aluminum beam will deflect much more. This is an important issue. Of course, the strength. Let's look at different materials. We can cover each other. So in some aspects, if we want to strictly control the deformation, later we can see the places where instability needs to be controlled, we should use steel. Steel should be used in areas that need wear resistance. In places with head contact, steel should be used. Of course, how steel and aluminum are combined and how they work together, this is another topic altogether. So there's also the issue of our trusses, which involves the strength analysis of trusses and design issues. Let me briefly introduce it. Trusses can essentially be broken down into rods, all of which form a rod system. These rod systems in a steel frame system are generally subjected to tensile and compressive stresses, the issue of tension and compression, the issue of bending, the issue of torsion. Let me briefly explain. Tensile and compressive forces are clear to everyone, so I won't go into that. When pulling a rod, the best material for this is one that excels in tension. The best material for tension is the one you would pull. Its stress is what? It is uniform stress. I won't elaborate on this. As it was just mentioned, the main issue in tension, the main issue is we cannot let it exceed the plastic limit. Its stress, its safety factor, the safety factor is generally between 1.2 and 1.5. If your calculations are more precise, it can even be lower. No problem. In extreme cases, we can actually use it to this point. Did you see that line earlier? In extreme cases, we can actually use it up to this position. In extreme cases, we can use it up to this point, use it up to this position, so it will not break. However, in order to maintain the integrity of the entire structure and to minimize deformation, small deformation, we cannot use it to that point. This is how it works. Remember the safety factor. For tensile issues, the safety factor is calculated based on uniform stress. It's based on uniform stress, then its safety, it needs to ensure its stress is smaller than the plastic limit. That's sufficient. Now the key point I want to talk about is this. In stage structures, the most important issue in frame structures is what happens when a rod is compressed. What happens under compression? When compressed, it first generates a uniform compressive stress, which is no problem. This is fine. This uniform compressive stress, we also need it to be less than the yield limit. For materials like steel and aluminum, these are typical isotropic materials, no problem. But if we are stepping on a very short aluminum sheet. This is no problem. However, if the main structure is an aluminum rod, a very long and slender rod, what will happen? There will be instability issues. This instability problem is unique to slender structures or thin-walled structures. A characteristic issue. One problem. Look at this kind of structure. Like this structure. If it's under compression, strictly speaking, the pressure will pass through its center of mechanics, allowing every section and every point to experience uniform pressure. It will not have any issues. However, unfortunately, two problems are absolutely inevitable. The first one is that every structure we make has defects. For example, you take a sheet of paper, the sheet of paper looks flat, but it is not flat in reality. It has defects. This is called a geometric defect. From the smallest defect, it will first generate significant compressive stress. This leads to buckling and collapse. The second problem is any kind of applied load. Even with an ideal applied load, it is impossible for the load to be perfectly aligned with the center of mechanics. There will still be mechanical deviations. First, it might not pass through the center of mechanics. Second, if it does pass through, it might not align along the axial line. So these issues can cause, all could lead to what? Making every point from individual localized points first reaching the yield point, and after yielding, triggering the collapse of the entire system. If you look closely, you'll see this. It's hard to tear it apart. As we just mentioned, to tear it apart, it must reach sigma D, the maximum sigma. But compressing it is very easy. The force is very small. It just collapses. It collapses immediately. So for such a thin-walled structure, for such thin-walled structures, for such slender structures, we must consider the instability problem. Also, this diagram, we can tell that about this topic, this is my own research result. I studied it when I was at Cambridge. It took me more than a year. This thing, it's the buckling of a local rod. Can you see it? We have a straight rod like this, a very, very standard rod. When compressed, it deforms like this, deformation. But if we have a small dent inside, a small dent made by a hammer, just a tiny dent, when we compress it again, you will see what happens. It will immediately exhibit this behavior. Of course, different dents at different points will create variations. This situation will occur. The force needed will be much smaller. Can you see this? It will be much smaller. An incomplete structure, an imperfect structure, roughly looks like this. Look here. The load-bearing capacity of these two will differ greatly. The load capacity is much lower. So as previously mentioned, I just explained this. The cause of this issue is one thing. It's due to the loading being off-center. Another reason is that it originally had a structure. If you think about it, if this plate remains vertical, this would not happen. For example, if the column is installed not vertically, this situation will also occur. So this kind of rod, is there a quantitative explanation? Yes, there is. First, look at the table on the right. It uses the formula derived by the great mathematician and physicist Euler in the early 20th century. A great mathematician, Euler's derivation. What is it? This is it. When a rod compresses like this, it must have a critical pressure. If the rod is perfectly straight, it will collapse after reaching a certain point. It will inevitably buckle. It will inevitably become unstable. It calculates a value, this value. Take a look. You don't need to memorize this. Actually, you already know this. Look here. The critical pressure relates to the critical pressure is proportional to this elasticity. For the same structure, steel's compressive performance and its shear performance is 3 times higher than aluminum. 3 times. So for columns, if you're not concerned about the cost, ignoring this, steel is better than aluminum. In column structures, steel is definitely better. There's another factor. Length is another factor. Look at this. This length is inversely proportional to the square of the length. So if we make the column thicker, the weight above will shift downward, moving the load-bearing position down. This greatly improves the stability against buckling, right? Isn't this the logic? Of course, in this case, this is the position. Look at this A. What is this A? It's the bending moment of inertia of this cross-section. The bending moment of inertia is of this column. It's the 4th power of the width of this column. If I double this, its bending strength. And its buckling resistance will increase by how much? It increases 16 times. This is the idea, right? So if our column is like that, make it a bit shorter and a bit thicker, steel will be better. There's another parameter which might be quite useful for your installation and is very instructive. Can you see this? These are different installation forms. Different installation forms. The coefficients at the bottom are different. Which form is the best? It's this one. This one is the best. Both ends are fixed. Actually, it's unlikely to fix both ends. The top one can't be completely fixed. The bottom one I can fix completely. But now this one end fixed and the other, hinged, is also good. This is 0.7. Can you see this? It's also good. So if both ends are hinged, it's just using a single rod, directly using a rod, a bamboo pole, directly planted in the ground, and then compress it from above. Let's see how much this is. This is 4 times. So the greatest characteristic of our installation columns is, remember one thing, which is to anchor the foundation securely. A firmly anchored foundation is better than anything else. Of course, if you can secure the top as well and prevent it from moving back and forth, even though I can't make it straight. But it's still good that it doesn't move back and forth. So how do we prevent it from moving back and forth? The best way is to use a tension rope, tighten it, and fix it in place. Now, according to what we've discussed above, the earlier concept actually represents our ideal. The rod is very straight. But if there are defects, as I already mentioned, so we conclude this concept, which is of instructional significance for your future installation for slender rod structures, you must consider the instability issue. Therefore, we must try to fix at least one end. At the very least, one end should be fixed. One end fixed, the other end must be tightened and locked with a tensioning device to fix it. Another point, besides general considerations, under the premise of meeting the needs, we should aim to lower the height as much as possible. Try to reduce it, minimize the height. By doing this, Another point, if your structure is sturdier, using steel will make it much better. Of course, other forces, such as bending forces, I won't elaborate. As for the bending forces, there's one thing, bending forces. You'll understand the stress distribution. Bending forces, for example, this rod beam, we use a solid rod, and the core at the center is at the center cross-section. The material in the middle is basically ineffective, no effect, and low efficiency. So now, to improve efficiency, H-shaped steel is produced. Producing H-shaped steel. This is something from my field of expertise. I'm the one who made this H-shaped steel. When the H-shaped steel bends like this, take a look. When it bends like this, the two wing plates are playing a role, and the middle is empty. Essentially, this improves efficiency greatly. Just understand this concept. If you in the future think about this rod, your cylindrical pipe, you can adopt such a cross-section. This type of cross-section. Of course, for our structure like this, because it's already a hollow structure, and naturally there won't be this issue. Since everyone can now understand, through this example, we can also understand why this rod of ours in the future, when beams are placed flat, they will experience bending. Why? Because these two main pipes are made so thick, and the middle is hollow. This also makes sense. It makes sense. Another point is torsion. For torsion, this type of rod of ours has to bear the load. I can tell you, don't be fooled by the appearance of our truss units looking so sturdy. I can tell you, its capacity to withstand torsion is very poor. We generally avoid generating such torsion. We avoid torsion from happening. Avoid torsion generation. What does this mean? Your hanging items, the structural connections, etc., its center of mass must pass through its geometric center and try not to let it be misaligned. Point 5. Let's talk about the design of trusses. The design of trusses. The basic principles are quite simple. This is the case with any structural design. Sufficient strength, sufficient stiffness, stability, good seismic performance, and so on. First principle. So how do we achieve this specifically? What are the requirements? Actually, we have the first principle, which is the stability principle. The design of trusses and steel frames has one key design feature. That is the triangular design. This is the structure we have here. When I look at a truss, there should not be any structure or any angle that forms a quadrilateral. This is not good, it must be a triangle. For example, let me explain. If everyone looks at this, this is a frame. If we take this frame out by itself, it forms a quadrilateral. It is very unstable. If I push it like this, it could easily fall over. However, in the middle, if we add a diagonal brace here, it changes to a triangular structure. Now this structure is much better. Everyone can see, if I push it, what will happen. Whether it's welded or hinged, hinging is no problem at all. Welding is fine too, but the strength isn't very high. So what happens if we add a diagonal brace here? If we push it like this, what happens? The structure will be in compression here and in tension here. If I push it this way, then this part will be in tension. This ensures that there will be no deformation and its stability is optimal. So in this design, there should not be any situation like this from any angle or position. For example, this rod presents such a problem. But to avoid this issue, everyone can see this area has been reinforced. If you look at it from this angle, it almost looks like a hollow quadrilateral. When viewed axially, if this area is missing, no matter how strong other parts are, there is a very high chance that if it's placed on the ground, a kick could collapse it. Of course, I'm exaggerating here, but if we add this reinforcement, it would be much better. Of course, if we also add a diagonal beam in the middle, the diagonal brace would improve it further. First, stability principle. Try to use triangles wherever possible. Another principle is the intersection principle. The intersection principle means that when we add these rods, we want them to function properly. Can everyone see this? These internal rods are meant to be effective. The points where these rods intersect must be placed along the center line of the main beam. Moreover, these intersection points must lie along the center line. Regardless of how large the forces are, there will be no bending at these points. Everyone should know, we've already mentioned this. Our rods are best at tension. Compression and bending are not as good. Also, for example, you can imagine if you're installing it, there's another point. You might often encounter a problem. We need to hang something at this spot. What should we hang here? A very heavy object. Where should we hang it? Take a look. Is it okay to hang it here? No, we must hang it as much as possible in this position. Take a look. This rod has a crossing point. Can you see it? The crossing point of the three rods is here. We should try to hang the load at that point. This way, the bending produced in the whole structure will be the least. Of course, there's also the principle of efficient material usage. Efficient material usage means we try to take a look. Sometimes it seems uncoordinated, like these rods. We actually put as much material as possible on the two sides. Why? Think about it. If this beam is placed horizontally, it will definitely be bent. The material at the outermost part of the bend, the highest point, the lowest material at the highest point, it performs best. If it is under compression, it won't be a problem placing it here. If under compression, place it here, it will increase the cross-sectional dimensions and increase the moment of inertia. In this way, it can enhance its bending resistance or improve its resistance to instability. The last point regarding the module design mentioned earlier, what about the design of the stage structure? Actually, the design principles for stage structures are the same. Its requirements are the same: strength, stiffness, and preventing excessive deformation, as well as good stability. There's also another point regarding the overall structure, which is the dynamic performance, wind load performance, earthquake resistance, etc. Because for our general modules, there is no such requirement. But for our entire framework, this requirement must be met. To meet this requirement, we need to do this specific work. The first is strength mixing. It was just mentioned. The strength mixing was just mentioned. Next, stiffness mixing. You can't have excessive sagging. It won't be able to withstand it. Next, stability. The issue of stability. You must remember, even now, take a look. I see that people from Guangdong really enjoy outdoor cooking and camping. They go outdoors, sit outside, and have some tea. Even the canopy, if you only pull one pole or only stake one pole, it won't work. What do they use now? They must use a strong line to pull it. So any such thin-walled structure, like a frame structure, must have a root. The concept of a root is simple. After installing the frame, you push this way. For example, with something like this. Take a look. After I add a root, push in any direction, push in this direction, will the tension increase here? This will prevent such deformation. Now this thing here brings up a problem. Now take a look. What's wrong with this structure? It doesn't have a root in this direction. That makes it very easy if a strong wind blows in the future, or if it faces any excavation, it will easily collapse at that spot. So the key task of our roots now is to prevent it from tipping over to one side. There are many methods to add roots. What should we do to add roots to this thing? It's simple. Adding roots to this is easy. This is still a wall. This wall has high strength. If I hang it on that wall, is it also rooted? Another way is to pull it in 4 directions. It must be tightened with a tension lock. Pulling it with a tension lock, like this. As for the wind load issue, that issue has already been discussed. We won't mention it again. Now regarding strength calculations, there's a problem here. It's about strength and deformation calculations. Such structures are relatively complex. In the past, we initially used a bit of a different method, a manual theoretical calculation method, using structural mechanics. However, this method is becoming increasingly difficult as structures become more complex, so I'll briefly introduce the issue of strength. Design. What are the traditional methods of strength design? Anyone who has studied mechanics knows. It's called elastic mechanics. But elastic mechanics is too complicated, so it was eventually simplified. Simplified into what? Material mechanics. To those who study mechanics in school, it seems like nothing. It's too simple. It's oversimplified. In reality, material mechanics, if you go back and look at structural mechanics, can only calculate stress and deformation for a few cases. There aren't many types. You can calculate no more than 5 types. Axle, think about this. Beam, if tension, I stomp on a potato column, and crush it and break the potato, but that's it. Can you describe the shape of the potato? Why can't we calculate it? It's simple. It's because it's geometric boundaries and force boundaries. Can't be described by mathematical methods. I've said a lot, actually. Many of these things were summarized by Shinestage. Thank you all.